Okay, so we continue on with our class examples for derivatives. And so example 2 says that, again, let x of t denote the position of a particle in meters, t seconds after it begins moving, where this time our function is x of t is 1/3 t cubed minus 5t squared plus 21t plus 10. And the things we want to determine here are the position and acceleration of the particle when its velocity is 0, and to sketch a plot of x of t. Okay, so we start getting used to this problem. We've got a function. We know x of t is the position, v of t is the velocity, a of t is the acceleration. We want to find when the velocity is equal to 0 and know what the position and the acceleration are at those, and then we'll use that to sketch it. And so we start with our position function. We know v of t is going to be the first derivative. And so we're just going to go ahead and get that function first. And again, it's a polynomial. And so we use the power rule. So we just multiply by the power, subtract 1 from it. So 3 times 1/3, we're going to get 1. So this term will just end up being t squared minus 2 times 5 is 10. It's now t to the first plus 21. So again, as we've gotten more comfortable with this, we can skip writing all those steps. We can calculate these pretty quickly. And then if we take the derivative of the velocity, we get the acceleration. Derivative of that is going to be 2t. The derivative of that is going to be 10. That's going to be the derivative of that is going to be 0. So we can get those pretty quickly. What the velocity function is, and I'm going to single underline just because we're going to refer back to these quite a bit, and what the acceleration is. All right, so now we want to know v of t equals 0. So that means that 0 equals t squared minus 10t plus 21. We can solve that any of the ways we remember back from quadratic functions. Again, quadratic formula will always work. Factoring can be easier if it works for this one, and it will. Actually turns out we can do this as t minus 3 times t minus 7. So t equals 3 seconds and t equals 7 seconds are my two solutions, where the velocity of t equals 0. So for t equals 3 seconds, x of 3 is 1/3 times 3 cubed minus 5 times 3 squared plus 21 times 3 plus 10. Work that out, I get 37 meters. And then to determine the acceleration at 3, I would just plug it into our acceleration function, which is right there. 2 times 3 minus 4, I get negative 4. And I'm not so much worried about significant figures in this one. It didn't tell me exactly where I wanted to round to. These do come out as exact integers, so I could put as many zeros as they require after it for that. So that's where we're at when t equals 3. We would do the same thing for t equals. So I'll determine it for the point at 7, which was our other solution we found here. We get that x of 7 is 26.33 meters, and the acceleration is 4 meters, positive 4 meters per second. One of the things we can know about that is we talked about previously these ideas of local max and local min. So yeah, where these equal 0, we're going to have one of the two, and the way we can tell which one they are is if this is negative, then that means that's going to be a local minimum, a local maximum. And this is going to be a local minimum. We don't know if it's the absolute or not. We just have to kind of sketch things and see how that goes, or we'd have to determine all the values that could happen in there. So part B asked us to sketch it. One thing, other than the points that we just found, another thing that would help us sketch it is thinking about where it starts at. So I went ahead and plugged in at time 0. Everything's 0 except for the last number. So we know it starts at 10 meters. And then we can use that to kind of guide us as we go through here. It would also be great if we knew where it crossed the x-axis, but since we weren't asked to do that, I'm not going to try to add that onto part of this problem. So in terms of making our sketch, we know a few things. We know 3 points. We know at 0, it's 10. We know at 3, it's 37. We know at 7, it's 26. We also know that those are local max and local min. So we know around this, since it's a local max, that we're going to curve down. So it's going to look something like going up to there, and then when it reaches there, it's going to level out because the derivative is 0, and then it's going to start curving down. Around this area, though, because this is a local minimum, we know it's got to be curving up. So somewhere in here, this has got to curve up, and as it leaves here, it's going to be curving up. And so we don't know how far it goes. So we know this one happens at 3:37. We know that happened at 10. We know this one's at 7 and 26.33. We know somewhere in here it has to actually change which way it's curved, and we can actually figure that out if we went through and set the acceleration equal to 0. It actually turns out to be at 5 is an inflection point. It's where the curve changes from going down to going up. Not a max or a min, but the second derivative, the acceleration is 0 there. So we have that. So should make sure to have units on here, time in seconds, x is in meters. Yeah, and that really gives us a nice little sketch of what's going on. Again, these aren't absolute max, but they are local max and local mins, as we can see there.